This program is being presented to you by the WE-Heraeus International Winter School on Gravity and Light.
So good morning and welcome to the International Winter School on Gravity and Light here at the Johannes Kepler University in Linz. We're now joined by 50 participants from all over the world for the remainder of the school, for the actual physical part. And we'll start with lecture 13, where the first 12 lectures dealt with the mathematical foundations of general relativity. And now the character of the course will change. We will now employ the mathematical tools we've introduced in order to describe relativistic spacetime and general relativity. So that means now we need to argue about why we choose which structure, and these are rather vague arguments because it's about physics, and physics is more complicated than mathematics. Because in mathematics everything is clear. It's just self-referential, and that is exactly its power, that mathematics per se has nothing to do with the world, and it wants nothing to do with the world, and exactly that is its power. Now in physics that's a more dirty subject, because you need to relate your notions to the world, and at the end you need to make predictions. So a lot more hand-waving and a lot more arguing is required. Having said that, of course we want to reduce that to a minimum. Nevertheless, we still want to develop as consistent a set of notions as possible in order to meaningfully talk about what we are talking. And of course, the picture we're going to present may need revision one day. Maybe we already do have the experiments that require that we revise the theory, and nobody at the moment knows how deep this revision will go. But of course, in order to surgically change the theory somewhere, you need to understand the old theory, the standard theory currently everybody is working with. So this is the theory we're presenting here, and only towards the end of the school I will go into some more detail about how this theory might be changed, and if you go about that, how this might be done. So the topic today is relativistic spacetime, and if you recall from lecture 9, the definition of Newtonian spacetime. There we had a set equipped with a topology such that it was a four-dimensional manifold. We equipped it with a smooth structure and a torsion-free connection, and additionally a so-called absolute time, and this absolute time was a smooth function on the four manifold. And there were two compatibility conditions. No, there was one definition on having really time slices, that is that the gradient of this absolute time function nowhere vanish, and the second condition was that time flow uniformly, that nabla dt was 0. If you recall this definition of Newtonian spacetime, and at the same time the definition I gave you at the beginning of this lecture course in lecture 1, and the definition of relativistic spacetime, I gave in lecture 1, so actually before lecture 1, which at the time may have been quite incomprehensible, but now it no longer is, and I no longer write down the words because we now know better. We can write down this is a manifold, a topological manifold of four dimensions. We find a smooth atlas for it, and back then we said it's equipped with a torsion-free connection. Excellent. Torsion-free. So far it seems the same, but then for a manifold, space-time manifold, a relativistic one, we have two more structures. So here we had this absolute time, And here we have two more structures. What are they? They are a Lorentzian metric on the manifold. Lorentzian metric, and I remind you, we had the signature convention plus, minus, minus, minus. And the T here is a so-called time orientation. And I'll tell you in a second what that is technically. So, but what I want you to observe is that what the role played in Newtonian space-time by the absolute time function is now played by the interplay of two additional structures, or two different structures, a Lorentzian metric and a time orientation. So first, time orientation. What is that? Because all the other notions appearing in here, and in fact appearing in this longish definition I provided at the beginning of the lecture course in lecture 1, all the remaining concepts here are already clarified. You know what a Lorentzian metric is, a connection, and so on. So what's a time orientation? Definition. Let M, O, A, G, we don't need to talk about the connection yet, we just look at this, a Lorentzian manifold. And probably we want an oriented atlas. So we take an oriented atlas. Later on we need that. Let this be a Lorentzian manifold. Then a time orientation is given by a vector field T. Okay, so we're relieved. This is nothing more complicated than a vector field, this T, by a vector field T, that A does not vanish anywhere. So it's a nowhere vanishing tensor field. And that second has the following property, that if you calculate G of TT at any point in space-time, the result is always positive. So let me draw pictures here. Let's go back to Newtonian space-time first, and then to relativistic space-time. Yes? Pardon me? Oh, does not. Yeah, I missed it. Thank you very much. It does not vanish. Otherwise, it's rather pointless. Thank you. Okay, thank you very much. So let's look at the situation. So let's go back to Newtonian space-time. In Newtonian space-time, you go to a particular point, say this one. So it's the four-dimensional space-time manifold in Newtonian physics. And at this point, the absolute time function has a certain value, right? So if I have the absolute time function yellow here, it has a certain value, and because it's smooth, it will have the same value elsewhere. I'm just drawing a 1 plus 1 two-dimensional picture of Newtonian space-time, okay? So this would probably in a three-dimensional picture, which is still one dimension too little, would more look like this, and this point lies in here, and this is where t is constant, okay? But I even go down a further dimension and look at it like this, okay? In order to draw diagrams. So I reduce the picture by 2 dimensions. So this is this, and now you know that the gradient of the dt, it's a covector, it's not a vector. So one is tempted to say this is the gradient, well, at least if the next level line, so say this was t equals 1, if this goes like this, then you would say this is the direction of the gradient, but we know that the gradient is a covector. And in fact, the gradient is best understood as this little plane attached to here, okay? And what this allows you is the definition of a future-directed vector. So recall. a vector x in Newtonian spacetime was called future pointing or future directed if dt of x is greater than 0, which meant that any direction that was up here, anything here, any vector in this half space, and this is a picture in the tangent space, right? So you have a point here, and this little plane here, this already lies in the cotangent space, an element of the cotangent space, and this shaded area is that subset of the tangent space at this point. So let me say this is a subset of the tangent space at this point, where all the vectors lie that are future directed. Okay? And the ones that lie on here, they are annihilated by dt. That's the standard theorem. And the ones that point backwards, they have a negative sign under dt. Okay? So these are the future directions where you can go. Okay? Now, if you draw the same picture down here, what you get is the following. First of all, you start from a point. And now the first thing is, you do not have an absolute time function. You just don't have it. What you have instead is a Lorentzian metric. The Lorentzian metric provides in each tangent space. So if I again draw now a picture in the tangent space at that point, the metric, the Lorentzian metric, you know, gives you a structure like this in a tangent space. We did this also in the tutorials, I think. Okay, this is what the Lorentzian metric gives you, and we now would like to have a similar definition because these future directed vectors were important because we said particles are always have world lines in Newtonian spacetime whose tangents are future directed. Okay, we're now going to talk about future directed particle world lines, but we would like to restrict to particle world lines whose tangent vectors lie inside this cone or possibly on its boundary. But they shouldn't run backwards and they shouldn't lie outside. The motivation will be to go from here to here, that we want to implement the idea that no massive particle can overtake light. Okay? Here you have future pointing tangent vectors, future pointing velocities, which can have arbitrarily, well, in quotation mark, high velocity. You know, velocity is a vector. What's a high velocity? If we haven't a metric yet, let's not talk about this, but that's the intuition. And so here we're interested in distinguishing one half of this double cone. So all the vectors that lie, and of course it continues, right? But the second half we're not interested in. We really just want half a cone, not a double cone. For the same reasons, we up here in Newtonian mechanics only want a half space. So we want to get rid of this guy. So how do we do that? Well, we have here the metric and this time orientation, and if you look at this, you have a metric at every point of the manifold. You have a metric and hence in every tangent space at every point, so also at another point Q, you may have another cone. Okay? And how dare I write only the half cone, because what about this half I just eliminated? So these are pictures in different tangent spaces. This is a picture in TQM. Okay? So the cones live in the tangent spaces. They don't live in the manifold. They live in the tangent spaces. Well, the point is, of course, this vector field T I introduced over here, this time orientation. First of all, the G gives you a double cone. But then if you have a vector field with that property say, a vector that's inside the cone here, and here it's inside the cone there. And if you emphasize that it is a smooth vector field, then it's clear you wouldn't all of a sudden flip from here to the opposite cone, but this would be smoothly chosen. Okay? So the combination of a Lorentzian metric and a time orientation gives you a distribution of cones over all the tangent spaces in your space-time. As much as in Newtonian mechanics, the absolute time gives you a distribution of half spaces of the tangent space everywhere along the space-time manifold. Okay? Now, in Newtonian theory, we could always introduce a stratified atlas and so on, so that it always looks like you have the equal time function like this, and then from wherever you are, now again a picture in tangent space, these are the future directions, right? Here, generically, it won't be possible to find an atlas such that cones all stand upright. But anyway, the cone standing upright or not is an artifact of the chart you chose, okay? Okay, anyway, so this is the basic idea. I tried to convey the motivation to change an absolute time function to this combined structure, but I will now make this more precise. So in particular, let me emphasize, I did not argue that in Newtonian mechanics you have a metric in 3 space and now we have a metric in 4 space. Well, that's all true. You can also introduce here a metric if you wish at some stage in inertial systems and so on. But the first and foremost task of the Lorentzian metric is not to measure any length. The first and foremost task is to produce these cones. Okay? Good. So that's the time orientation. This definition of relativistic space-time, and from now on I will only refer to it as space-time, and I will only say Newtonian space-time if we talk about the non-relativistic version. Yes?
I understand from the cones that we need the metric G to give for a velocity vector the sign basically. But I don't see how the T comes in there.
Okay, okay. So the question was, what exactly is the role of the T? Well, if I just provide you with a manifold with a Lorentzian metric here, then you go to an arbitrary point of the manifold, and in the tangent space at that point, you get the following structure of vectors, where the vectors lying on here satisfy gxx equals 0, and the vectors in here satisfy gxx greater than 0, but also the vectors in down here satisfy gxx greater than 0, and all the vectors lying outside here satisfy gxx less than 0. So by requiring that a vector have positive sign, if this is my sign convention, I select the interior of this upper cone and the interior of the lower cone. However, in order to now make a particle definition, which I'm going to make, I want to talk about future and past. I want particles to run forward rather than backward. So I need to eliminate one of these cones. But the metric doesn't distinguish between them. So I need an extra choice of a vector field that lies either inside here or inside here. So I choose the T and say the T is this one. Then this chooses this part of the cone. That's enough information to say which part I mean, and I can eliminate that one. And then I get a space-time picture, an objective space-time picture, where in each tangent space of the space-time there lives a half cone. That's the role of the T. So this definition of space-time has been made to enable the following physical postulates, or rather enable us to stipulate the following physical postulates. And so that's the first physical postulate. 1, the world line gamma of a massive particle satisfies by this postulate two conditions. First, it lies inside the cone, so the velocity, the tangent to it at every point along the curve lies inside either the forward or the backward double cone. But what is the forward and the backward double cone? Second condition, G gamma of lambda T, comma, V gamma of lambda is also greater than 0. So the picture for this is you have a trajectory in space-time in M, a smooth curve in M. And now what you need to check is whether at every point of the curve, say at this point, it is true or it is not true that the cone that lives at that point anyway, okay, you need to look, how does the cone look like? Well, you need to look at the tangent vector to this curve. I draw it like this, although I shouldn't, it's a directional derivative. So we're starting to do a tangent space picture, right? So let me be precise here. And as soon as I start drawing this, I'm talking here about elements all of a sudden in the tangent space, whereas, of course, the curve was running in the manifold. That this tangent vector here lies inside the cone that we have at this point. So the cone, however, is given a priori because I know the space-time, and I know it's one of the two cones, whether it lies in the cone in which also the T lies, because then the inner product of these two with respect to this metric will be positive. If the T had selected this cone, then the inner product of this velocity with this T under this Lorentzian metric would be negative. Okay? So in this sense, this T is used all the time. And so you check, okay, at this one point, the tangent vector lies inside the local cone. You need to check whether at the next point, I just draw yet another one here, whether this tangent vector still lies within the cone. But the cone at that point, right? So it's very important that space-time consists of a half cone in each tangent space. Which half cones? Well, the ones that the metric, the Lorentzian tensor field tells you have. Yes?
You have just said inner product, but in one of the tutorials we had the question of the metric. Can we use to define an inner product, and this was wrong. Is it here an inner product because of the T, or is it not?
Okay. It's not an inner product in the sense that it's a positive definite inner product, because this has the wrong signature. If this had positive signature throughout, it would induce an inner product on each tangent space. Now this induces a pseudo inner product on each tangent space. It shares all the properties, but it doesn't have the positivity. And in certain directions, it satisfies an inverse triangular equality rather than a triangular equality. We'll come to that. Okay? So if I say inner product, I mean here Lorentzian inner product or pseudo inner product. Okay, so this is for massive particles, and the postulate P2 refers to massless particles. The world lines of massless particles. And note that in Newtonian mechanics, we couldn't talk about massless particles. In Newtonian mechanics, every particle has mass. F equals ma, right? You have to have a non-vanishing mass. It's in relativity that you can have massless particles. So world lines of massless particles satisfy A, 1, that their velocity along the curve at every point, so this is at every point along the curve, of course, at every point along the curve, that the velocity at every point along the curve is equal to 0. That means the tangent vector lies on the boundary of the cone, but the second condition is again formally the same. This is V gamma gamma of lambda, V gamma gamma of lambda. With the t, it must have positive, pseudo inner product at each point. Okay. Okay. So the picture for this is, I now go the other way around. It's also maybe more logical. So say picture overall. Say you have a Lorentzian spacetime. And I'm now trying to draw the objective spacetime, whatever that means. So at every point, I have a little half cone. Why would it not look like this? It could, right? Why not? Okay. Now, this is the trajectory, the world line of a massive particle. Perfect. Yeah?
I want to ask the second condition in the P1.
Yes.
This tells us that we choose the cone where the vector lies within.
Mm-hmm.
But how do we know that if that's the future cone or the past cone?
Because the T says so. No, it's a very good question. It's a very good question. We need to decide what is future and past, and we need to divide it. Relativists came up with no better idea than to say, choose it. However, because the T is a smooth vector field, once you start choosing it at some point, it's more or less determined how it works in the other points. Otherwise, you just exchange the notion of future and past. Okay? The question of what the arrow of time is, whether time runs like this or like that, you can have answers to this from statistical physics, and you can have other ideas. In general relativity, this is no further resolved. We say this is what it is. We have such a time orientation. It's different from the oriented atlas, right? It's a time orientation. It's a choice of a half cone. Okay? But the smoothness makes this less arbitrary than it may seem. Okay? Yes?
So can we always get that? I mean, we had this one example on the sphere where you couldn't choose a vector field which was not vanishing anywhere.
Yes. The sphere also cannot carry a Lorentzian metric. So every smooth manifold can carry a Riemannian metric, but not every smooth manifold can carry a Lorentzian metric. So there are obstruction theorems that tell you those smooth manifolds can and those can't. The same is true with time orientation. Okay? And we'll come to further constraints. So by requiring that these structures exist, there is no guarantee that for any underlying choice you can always put such a structure on top and it exists. But then the underlying choice is also excluded as a spacetime manifold. So for instance, we could think of a two-dimensional world and say, oh, it would be funny if the sphere is orientable if we took the S2, the oriented S2 as a smooth manifold and considered this as space-time. So we just need to find a metric and a time orientation. Well, the point is you don't find a Lorentzian metric. So the S2 as an underlying smooth manifold can never be made into a space-time. Okay? So in this sense, there are constraints that come by adding further structures. Can you really add them? Okay. Yes. And so you can enter the business of deriving theorems on what can then still survive at the lower level and what not. And of course, all of that exists, right? Okay. So here we have a massless particle, but I should also show you a massive one. No, we have a massive particle. I now show you a massless particle. Well, a massless one would be this one here. Okay, we need a few more cones. Well, it's clear. I mean, this is just a representation of all the possible cones. They can also start looking like this, right? Why not? Okay? So that means space-time is really this collection of cones, essentially. In fact, 9/10 of a metric are determined by the cones. You can think about that, right? So claim 9/10 of a metric are determined by their by the cone. And only 1/10 then still needs to be fixed in, okay, 9/10. So if I say the spacetime is essentially a distribution of cones, it's almost right. Only 10% error. Good. So we have this. Aha. So, well, these are just postulates, but you see, these definitions and this motivation has a lot to do with these postulates, right? We do this in order to be able to talk about particles of one kind or of the other. However, all the difficulties one might have at first with relativity is that somehow in your head you still have this absolute time function somewhere. And you still can't wrap your head around it that the structure of your tangent spaces, that your tangent spaces at every point are now not divided in one half space and another half space, but that they're divided in one cone and not that one cone. Okay? That's all the problems with relativity. There are no others. If we follow the definitions we're now going to make, no such problem will arise. And of course, in a sense, if you think that this one half cone opens up more and more and more, let's say it does that somehow, don't we get a picture like this? Well, yes, right? So a cone is an object from linear algebra. It's a generalization of vector subspace. A cone is a space where the sum of two vectors that's in there is again in there, like a vector subspace, and where positive multiples of a vector are again in there. That is a stronger requirement than that any multiple of a vector is again in there. Any multiple in there gives you a vector subspace. Only positive multiples of vectors already in there are again in there, gives you a cone. Well, this is a cone too. Anything in there, another thing in there is in there, and positive multiples are in there. Negative multiples are not. These are cones, and these are cones. These are even convex cones. It's not such a big difference. It's just not, you could say relativity is, instead of having cones that are half spaces, you have cones that are proper cones, right? Okay. And of course, the whole idea is these particles, if you think in velocities, and I wouldn't, usually one would say nothing runs faster than the speed of light, but faster refers to speed, right? And we haven't talked about that quite yet, because we could measure we could measure the length of the velocity of the space-time velocity. We could measure the length of this v. I get a specific number, but that's not the velocity an observer sees. It's just the length of the space-time velocity. If we talk about speed, we mean what an observer sees in his laboratory. We'll come to that, okay? But the intuition is these guys can never overtake these guys, right? Okay, anyway, so that's the definitions. But obviously, in order to talk about notions we are more familiar with, namely what an observer sees, we don't know what observers are, right? In order to do that, we need to define observers. Definition. Is it? That's true. Thank you. Definition. So we're now always dealing with a space-time. What's an observer? An observer is a world line gamma with gamma g, v gamma greater than 0. I do not always write the gamma of lambda, okay? Greater than 0 and g of t v gamma greater than 0. So you say, like a massive particle world line. Indeed, observers in relativity are always observers that could be realized as massive objects because they have to carry with them a measurement apparatus or something, okay? An observer is a world line gamma with these properties. Oh, and usually one calls world lines like this, one calls them time-like. I don't like that. Time-like, there's no time in the game so far, okay? Let's get rid of this notion time-like, space-like, light-like. Let's not talk about it, because the like already tells you it doesn't mean what it says. Okay? So let's just not say it. Okay. Later on, you're allowed to do that. It's like swear words. If you have children, right? You tell them, don't say that. God damn it. Okay. So later on, you may reinstate that. So an observer is a world line gamma with this, together with, so it's not only a world line, together with a choice of basis E0, depending on the same parameter lambda on which the curve depends, E1 of lambda, E2 of lambda, and E3 of lambda. So we're talking about four-dimensional space-time. You can easily make a d-dimensional space-time out of this, of each t gamma of lambda m, where the observer world line passes. Now actually the precise formulation would be an observer is a smooth curve in the frame bundle Lm over m. Okay? Because I draw a picture. So this is a curve gamma in space-time. Yes?
I think there is a very important new point in it. Now we speak on four-dimensional manifolds.
Yes.
Because in the Newtonian picture, the time was a function, and we were staying with three-dimensional manifold. Is this correct?
No, the Newtonian space-time was a four-dimensional manifold.
But because the time was just defined as a smooth function.
On the four-dimensional manifold. And those direction or those level surfaces of the time where the absolute time is 5, that's a three-dimensional surface, and that is the space at time 5. So the Newtonian space-time manifold was 4-dimensional. Yes. Yes.
If you gave a basis in each point, it seems like ill-defined.
Pardon me?
If you give me a basis in each tangent space, you have a basis, a definition based on the choice of basis.
No, the choice of basis is the observer. Let me come to it. Let me come to it. So, there is also something missing here, if writing something here. So, the idea is the following. You have a word line that at every of its points lies within the half cone prescribed by space-time. Okay? And now you make here an additional requirement if you require something of this basis, but that still doesn't fix it. If the eighth basis vector at the position lambda and the bth basis vector taken in this inner product, if the result is eta AB, and eta AB is just 1, minus 1, minus 1, minus 1, is this collection of numbers, the rest are zeros, AB. So one could say they're orthonormal, but that would be more like a unit, but orthonormal as a Lorentzian metric, which means they produce this result. That's a requirement on the choice of basis. And it means, oh, and I forgot something else, okay? And this E01 is the same as the tangent to the curve. Okay, so what does that mean? That means that, for instance, at this point P here, P is gamma of some lambda 1, say, there is a tangent vector like this, and that one we would call E0 of lambda. Of course, an element of the tangent space. Okay? Should write this a little bit deeper here. Gamma of lambda 1 is the point P we're just going through. And then, so that's for the first basis element, I don't have a choice. I choose the tangent vector. And for the others, I choose further ones. And here I only draw 2 more of lambda 1. I only draw 2 more because my picture is at most 3-dimensional. Okay, so you need to think of this in perspective. And the idea is that they pairwise give either 0, no, pairwise they give 0, but this with this itself gives a 1, of course, and the others give minus 1s. That's how they're chosen. And you can always do that. Okay? And at another point down here, you have this one is fixed, but then you have 2 more, E1, E2. They are not fixed because, intuitively speaking, you could choose any rotation thereof, right? But you can no longer change the E0 because that one is fixed. Now you see an observer is a little more than just a world line. Yes?
Why did you put an index on lambda?
Because I wanted to say this in order to develop the picture further. So this is gamma of lambda 2, oh that's silly, lambda 0, lambda 0, lambda 0, lambda 0, because soon I'm going to talk about these two.
I think the one on the top is really lambda 1.
Yeah, that's right. I'm sorry. Thank you. Yes?
If it's written like this, an arbitrary curve doesn't necessarily have the tangent vector normalized to 1. So
Yes.
it's not quite... So is it always normalized to 1 by definition?
Yes, here we do that because that will help us later on. You can always do that because you can reparameterize a curve. And then we'll have to do with the definition of time that comes in a second. So this is intentional. So I could have specialized here already to 1, which is greater than 0, and that would be in accordance with this. Thank you for the observation. But that's exactly intended. Okay? Yes?
One more question. So basically, our basis extracts the signature of our metric. If we have GA, GB, with an eta, why
It must. It couldn't do anything else. You would never find a basis that is where this is diagonal and doesn't have this signature. It could be 5, minus 7, minus 3, and so on, but then you could rescale the vectors again. Yes, that's right. That's right. So that's the condition. A frame bundle, yes, I said precise, and that's something I didn't explain. A frame bundle is where you have a manifold, and at each point, P, you attach as a fiber, not the tangent space, but the space where in the fiber, a point in the fiber is a choice of basis at the point P, a choice of basis of the tangent space. So the fiber at a point no longer contains all tangent vectors, it contains all quadruplets of tangent vectors that constitute a basis. Okay? And then if you have, so if these are all possible bases here, and then you have a curve in the tangent bundle, a smooth curve, that actually helps you encode that from here to here, so this doesn't all of a sudden change to this, but this goes smoothly. If you want to say this precisely, you need to say it's a smooth curve in the frame bundle. Okay? But you can ignore that. The idea suffices here. Yes?
Would it be sufficient to say that the basis vectors as function of lambda should be differentiable?
Basis vectors as a function of lambda should be differentiable. Well, the question is what precisely that means. Because then you would need to have a map from lambda to where? Because for each lambda you go to a different tangent space. So maybe you could say you have 4 smooth curves in the tangent bundle. 4 smooth curves in the tangent bundle, yes. And then you could additionally require that they are always orthonormal in this sense. That would probably be a leaner way. Yes, yes. Thank you. Okay, so you see the physical interpretation as an observer is more than just a world line, because an observer will feel quite different, observe quite different, whether he's just, say, freely falling or whether he's freely falling and rotating. And how do you capture the rotating? Well, you can only capture it via the attached frame. Okay? But an arbitrary observer will just do something like this, right? And you need to say which observer you have in order to say, well, no, it doesn't do this, it goes like this or something like that, okay? Okay, but that's the abstract notion of an observer. And there come again 2 physical postulates. So that's P3, because we already had 2. P3 is a clock carried by a specific observer. And we'll call an observer always gamma comma E, where the E stands for this whole selection, right? A clock carried by a specific observer will measure a time interval. Well, we'll measure a time tau is a time tau integral from lambda 1 to lambda 0 to lambda 1. It's the ones I chose. D lambda square root of g gamma of lambda v gamma gamma of lambda v gamma gamma of lambda between the 2 events. So that's relativists' jargon. An event is a point in space-time. Between the 2 events, gamma of lambda 0, and that event is start the clock, or rather push the start button of the clock, because pushing is something localized in space, pushing a button, and in time. Okay, that's an event. Start the clock, and gamma of lambda 1 stop the clock. So if this observer decides to activate his stopwatch that he carries with him, and he switches it on here, he lets it run and he switches it off there, then the length of this world line in space-time as measured by the metric, which this is nothing but the length function, all right? The length of the world line in space-time has a meaning. It has the meaning of the time that the clock measures. Now this seems a rather arbitrary postulate. In fact, this is one of the nicest things that you can look at with a light clock. Maybe I explain that later. So this is very solid. And this defines what time this observer sees. And please note, so far in the discussion of relativistic spacetime, this is the first instance that the word time enters the discussion. You agree? I didn't talk about time, which means time is a derived notion in this context. I don't talk about time just like that. I talk about time as the time that a clock measures. Okay? Now you could ask, construct such a clock and prove it. You can. You can construct a light clock. I'll maybe come to that. However, time of an observer as a clock measures, and the clock is a clock that's carried by this observer. So this yellow path in space-time, this yellow part of the world line, is the history of the clock. There is nothing in this definition that suggests that another clock, taking another path, even from the same point, starting point to the same end point, but along another path, as long as it's a path that is also an observer, will show the same time. Is there any reason to assume? No, not a priori. Well, in fact, it will not be the case. Time will depend on the world line that the clock takes in space-time according to this definition. Okay? That's all. So if people say the concept of time is changed in relativity, that's right, because there is no longer one absolute time. You cannot look at the point in space-time like in Newtonian space-time. Do you remember? In Newtonian space-time, so compare, in Newtonian space-time, I could just pick a point, P, a single point, without observer, without a second point, without starting a clock and stopping a clock. I could pick a point, and I would know the time associated with that point. I would simply know it. Well, you can say, yeah, but you could rescale this absolute time. Yes, that you could do, but nevertheless, once you have settled the absolute time, an event comes at a certain time. And other events come at the same time. You have the absolute time function, and then you can ask, what's an event at the same time? And if you have two events, like our picture up here, this is just yet a derived notion, because you say, okay, this point P and this point Q, the difference in time, independent of how you go from here to here, and independent of what path your clock takes, it's always T of P minus T of Q. Okay? That's the Newtonian concept of time. Here, this is entirely different, totally different. There is no time associated to an individual event. There's not even a time difference associated to two different events. There's a time difference associated to a certain path that a clock takes between two events, and that clock is started here and stopped here, and then it will show this time. Yes?
So far, have we we've been talking about the real world or chart, or how do we know that it's chart independent?
This is all the real world, and you can see here, because I don't use any components. This is the metric, this is the velocity, this has nothing to do with components. I haven't written down a single component so far. And also the little cones here, they're objective. Because, say this is here and now where I am, this point, okay? And now I light a little light bulb for just a millisecond. Click, it blinks. And then it will take some time until the light has reached some member of the audience over here and some member of the audience over there, but it will go out in a spherical way, right? This impulse, this light flash. And well, depending on your frame of reference and so on, very roughly speaking, this is what goes out, but remember this is in tangent space, okay? So the light ray will actually go out more like, say like this, and the other one maybe like that if you have a very vicious space-time where the cones start, if the cones develop more like this, not develop if they are positioned like this, right? So the actual light goes along a null trajectory, and this is just the tangent at that point. So if I draw these guys, it's actually wrong. I should rather draw these guys, but then it all again depends on what frame of reference you're in, how these are tilted. But anyway, so I can make the experiment. I send a photon in this direction, in that direction, and the photon does what the photon does, right? And that is the velocity of the photon here and the velocity of the photon there is like the velocity of the bird, right? It's unimpressed by choice of chart. The position of the cone is totally unimpressed by the choice of chart, because it's an objective reality that at that point a photon sent in that direction will have that velocity.
That cone is a picture.
I see. Did you ask this question in the email with the real world? Yes. Okay, so there was this question, which is a justified question. I always talk about the manifold and all its objects as the real world, and then as the charts is kind of what we make of it. Now, of course, you could say, well, it's not the real world, it's a manifold, right? It's also an idea. But the point is, if we think about the real world as physicists, we think. That's what we do, right? We have no further access to the real world but to make concepts and then to make experiments that relate these concepts. So if I think, oh, there's a bird and it has a velocity, that's already thinking, because you can't see the velocity in the world. The velocity already is a concept, right? But this object has a velocity, but our idea of velocity is not chart dependent. It's only that in high school you're indoctrinated that all of a sudden you have to associate velocities with 3 numbers, right? That's what they teach you in school. But the concept of velocity that a child has nothing to do with these 3 numbers, right? So what you learn in school is already in a chart, but the concept of velocity is there independent of a chart. Okay? And that is when I say that's in the real world. That's our concept about the real world. Okay? Good. Okay. So in this sense, this is in the real world. Okay? And this is all a picture in the real world, and none of this formulation depends on a chart. Okay. Now, there's a certain amount of terminology that goes with all of that. You would call this tau the proper time. The proper time. Or the eigen time of this observer from here to here. But you call it proper time in order to distinguish it from the Newtonian time, right? But in this theory, it's just time. Time is what a clock measures. Okay, so that's the first thing. And let's make an example, an application for that. Application or / example. the example is take a space-time R4 with the standard topology and some smooth atlas for it, and take as G the G that's given by Gij in a chart X equals eta ij. Okay, and so we have an atlas that contains R4 times the identity on R4 as a chart. And if that exists and you have this, you can calculate the Christoffel symbols. Therefore, it follows gamma ijk in that chart are 0 everywhere. And the chart covers the whole manifold. That means this space-time, an oriented atlas if you wish, the space-time. Okay, and you choose a time orientation in the same chart. I is chosen as 1, 0, 0, 0, I, for instance. Okay, you have this time orientation, and of course from the G you can make a connection, but because this is 0 everywhere, the Riemann curvature will vanish. That means this space-time is flat, and we have chosen a chart in which it looks particularly nice. Aha, this situation is called special relativity. This situation is called special relativity. Or one should say it's the domain of special relativity. You have a flat space-time. But otherwise, special relativity is not different from general relativity. Not at all. Okay? And now you may consider two observers. And I give all of this in this chart because I need to write it down. So one observer is called gamma, and his world line in this chart has components that are lambda 0, 0, 0. It runs from 0 to 1. So if I'm in the chart, let's say it looks like this. Okay? Good. And you see, you take the derivative, you get 1, 0, 0, 0. That has certainly positive inner product with the t here, because we have signature plus, minus, minus, minus. So this is an observer. Then we have a second observer, delta, 0, 1 to m, who takes a rather more adventurous route. Delta x, that's the ith component. Delta x, the ith component, is lambda. No, it comes in two sections. Lambda, alpha times lambda, and alpha from 0 to 1 excluded both. 0, 0. I, if lambda is less or equal to 1/2, now we run up to parameter value 1, and here I get lambda 1 minus alpha lambda 0, 0, ith component, lambda greater than 1/2. And that should be, depending on the alpha, that should look like this. Okay? If the alpha is going close to 1, then, so look down here, you have a cone that is like this, and every point you have a cone. In this chart I've chosen, the cones everywhere stand upright, okay? That's essentially the choice that I have this eta here in this chart. In this chart. In another chart, the same metric may look different, but that's why I choose this chart, okay? So this is the situation, and if the alpha goes to 1, this one is going closer and closer and closer and closer to the boundary of the cone, but it doesn't hit the boundary of the cone, of course. It can't. Okay, if I let the alpha go to 1 or higher, then I no longer have an observer delta. So I have to do something like this. Okay, so you of course see where this is going. It's going to the twin paradoxon, right? There are two twins, they are both born. One just falls freely in space, and the other one also falls freely in space in another direction because the mother kicked him in that direction. Well, we're in space in a thought experiment, right? And then at some point he's being kicked back and then he meets the other twin again. Okay, you could also think of rockets and flying away and all kinds of stories. Okay, and so the point is we have to calculate what is the time elapsing of the clock that this guy gets for his birthday, and what's the time elapsing on the clock that the twin that was first kicked away shows on his clock. Okay, let's calculate. Okay, so tau for the gamma guy. Okay, tau gamma. Tau gamma, gamma, delta. How does this go? Is integral. We go over the parameters from start to end, is 0 to 1 in this case. We have to integrate over the square root of the g of the velocity. I immediately write it in this chart, gij. The velocity is gamma in the chart, ith component dot, gamma in this chart, jth component dot. Do you agree? That's what it is. Okay, let's quickly evaluate it. 0 to 1, d lambda. D lambda. Gij is this eta. Okay. And the gamma dot is 1, 0, 0, 0. So the only term that survives is the one here. 1 times 1 times 1 plus 0, 0, 0. So there's a 1 equals 1. Integral from 0 to 1 over 1 is 1. So, yes?
I think there should be 1 minus lambda in the path of delta.
Here?
Yeah, and the alpha outside the current.
What did I do in my notes? Probably you're right, because you had time to think about this. No, I had it like this. Okay. So, so let's see. Okay, so I want to go there, and I arrived here after time lambda half. I arrived at. I want to be at alpha times lambda. Okay, and then I want to go back. So I have arrived at alpha half because the time has half. Then I want to go back minus alpha lambda. Confused. Are you sure? 1 minus lambda and the alpha goes out? Is that right? So let's see. At 0, this is alpha. That's not good.
And 1 half only counts for lambda bigger.
Oh, that's right. Okay, so at lambda, yeah, but lambda big. Okay, so that means at lambda 1/2. You're right. Okay, so, sorry. At lambda 1/2, this is 1/2 alpha. That's right. And at lambda equals 1, this is 0 again. I think you're right. Thank you. Thank you. Yes?
Is there any subtlety because the observer does not have a smooth curve, or it's for the purpose of this, it's
No, this is because you're evaluating an integral, you can evaluate it piecewise. The curve, and so you can take out this point and you can make it smooth and it works the same. It's just this is the easiest to integrate, but the principle is always the same. Okay, that's right. Okay, so here you have 1. So for this guy, 1 year passes. 1. I'm sorry. Now the other observer has integral 0 to 1/2 d lambda of this expression. So we have to evaluate this first in this first part. This is 1 alpha 0, 0. This gives you a 1 squared minus alpha squared. Right? Then you do the second half, 1/2 to 1, square root. 1 squared minus Now we derive with respect to lambda, then only this term survives. That's minus alpha, so it's minus alpha squared. Correct? 1, and with respect to alpha only this is the minus alpha. Yeah, I think that's correct. And this is of course twice the same term. Okay, not surprising from the picture, but we're better safe than sorry here. So this is from 0 to 1 square root of 1 minus alpha squared d lambda, which is square root 1 minus alpha squared. And you see, if alpha is not 0, which we excluded because then it's the same guy, the time that this guy travels is reduced. It's only the square root of 1 minus alpha squared. And the closer the alpha goes to 1, the more this guy, we would almost tempt to say, approaches the speed of light. I haven't shown that yet. But the more he goes to the boundary of the cone, the more you can drive this time to 0. So if you only move away fast enough and come back fast enough, you don't age much, according to the clock that's being carried. Okay? Now this is of course the twin paradoxon, and the paradoxon is supposed to consist in the fact that what about relativity, right? But who talked about any relativity? This is the definition of time shown by a clock. But maybe at this point one gets very suspicious of the whole framework, because one says, I mean, how can that be? And indeed, if we take it seriously, so taking the clock postulate P1 or P3 seriously, one better come up with a realistic clock design that supports the postulate. You can say, well, you can tell me a lot about what a clock measures. What does a clock measure? And the idea, but we're not going to do this in detail, partly because I haven't introduced all the terminology yet, but it's quite useful to see the following. So assume I have two little mirrors. And I let a photon run from here to here. It gets reflected, goes back, and so on. It goes back and forth. If I draw the history of that, it looks like this in space-time. There's the cone at every point. The mirror runs inside the cone, but light runs on the boundary. Now here there's another cone. The other mirror runs inside the cone, but light runs on the boundary. Okay, let's say like this. And of course it's a clock, because it makes tick, tack. Okay? It's a clock. Now, very roughly speaking, if you bring these two mirrors closer together, it doesn't make tick-tack, it makes tick-tack, 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 tick-tack. You can be arbitrarily precise. It's a fantastic clock, it's a light clock, and it's so fantastic because it works relativistically. Light is a relativistic matter theory, we'll come to that, and so the working is relativistic. Now, you take another clock and let it run like this. So now lots could be argued about what the real distance of these guys is and so on. This is a very rough estimate, so I'm not talking about here and I'm not talking about here, but if I make them very small, that's not so bad. And now let's count the ticks here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 ticks. Now I do the same here. Let's say I start somewhere here. 1, 2, 3, 4, 5, 6, 7, 8, 8. There you go. It's shorter. It's a light clock. Okay. Yes.
Which time does clock measure? I mean, because this mirrors has some distance between.
Yes. Yes. So one has to talk about, if this guy moves away, what the distance of these mirrors is in the moving system. Yes. I said I haven't introduced all the terminology to do this, make this precise, but at this point I think the picture is rather helpful than only letting this abstract result here. Okay? Yes?
In the example before, did we make use of the chosen basis of the observer?
No. No. You mean the chart? You mean the chart here that we've chosen?
No, I'm just asking if we needed the chosen basis of the observer or not.
Well, I mean, if I want to write down precisely how the line should run, I prefer to go to a chart and I write down the numbers, okay? But the objects I calculate are independent of that.
I think he means the frame bundle.
The frame bundle. Sorry, no, please ask again. Okay.
I mean, we defined the observer as the
Yes.
pair of a curve
And this frame. Yeah, we didn't use that frame yet. We didn't use the frame yet. So the clock is only the length along the world line, independent of how quickly the frame rotates or not. Rotates in quotation marks. We'll get the notion of that. Okay, yes?
Each twin will see the other one move away, right? So
Yes.
how do we know why does one age more than the other?
Well, because of the clock postulate. Okay, that was a mean answer. So the point is you're trying to construct a paradox, right? And the point is, well, first of all, this guy has inertial motion and this one hasn't. So this one will realize at some point he has to be accelerated again. Okay? So that already, so you give both of them an iPhone and at some point the screen of the iPhone will change for this guy if he holds it like this, right? Okay. However, that's not the explanation for the effect. That's just the explanation why they are different. Okay. Sometimes it's claimed that all the effect is here in the acceleration period. Well, this is really nonsense, because for many reasons this is nonsense. It's just the total length here that counts. And then imagine I had done the following. Imagine I had asked the question, there's a twin going from here to here, and there's another twin doing this. Who has aged more? And it's a totally ill-defined question, because they have to reunite to compare their clocks. If not, then it depends on the state, or let's say, I do it even like this, say like this. Who has, but the other thing is also ill-defined. This guy here, in this flat space-time, okay, this is already pretty bad, like this. So this one will see all these points here in the flat space-time, all these directions as equal to his time. And this one will see all these as the points of equal time to him. So this one will say, now that I'm this old, how old is he? But this one will say, now I'm this old, how old is he? Okay? So the point is you can't do that. You need to reunite in order to compare. So therefore a statement like the whole effect appears here, I wonder from whose point of view. Right? You can't do that. You have to synchronize clocks and to compare them again at the same point. Why? Because if you're not at the same point, you don't even know when to compare them. Okay? That's, yes?
What would happen if they could somehow see each other during the movement?
Okay. Okay, I think all interesting questions, okay? The points, I think we're getting too far from what I wanted to tell you. No, it's not an excuse. I mean, of course, we could start discussing this and so on, but every discussion now would heavily rely on this being a flat space-time, because there I can really, what I did here, I can say these are the points of equal time. In a curved space-time, that's not even so clear. what that is. Okay, so there are problems of what's the distance, radar distance or not. In curved spacetime, this becomes all. I don't want to confuse you with flat space concepts, which we could now employ to make progress here. Okay, that's the point. So I think I leave it with these remarks at this point, and I have another important definition, or another important postulate. Postulate. Let gamma E be an observer and delta be a massive particle world line. Massive particle world line that is parametrized such that G of V delta is 1 everywhere. Why do I do this? Well, I parameterized world lines according to the time that a clock would show that travels with the particle. Why do I do this? Well, because then I save a lot of normalizing factors in the following definitions. And I can always re-parameterize a world line. So I choose to parameterize a world line by the time a clock carried by that particle would show. Why not? So I do that. Then the observer. Now let's make a further assumption. Assume or suppose the observer and the particle meet somewhere in space-time.
Do we assume that the observer world line is also parameterized?
Yes, that's already in the definition. That's because of the normalization of the frame. Yes. Meets, well, somewhere in space-time, meet, also in Newtonian space-time, is a space-time concept. Right? I was here, you were here, but we weren't here at the same time. So meeting is a space-time concept. Meet, that means that there is a parameter lambda 1 for the observer and a parameter lambda 2, or let's call them tau 1 and tau 2, for the particle where they both meet at the same point. So you have an observer that goes about happy observing here, okay, and a really fat, very massive particle happens to be where the observer is at a certain instant. Now this particle has a velocity in space-time v delta. Agree? This is the delta and this is the gamma. That's a space-time velocity, sometimes called a 4 velocity, because it's a velocity to the world line. Okay? But that's not the velocity we're talking about in real life, because we're talking about 3 velocities. Now, the observer, this observer, sees or measures the 3 velocity or spatial velocity. This observer measures the 3 velocity or spatial velocity of this particle as, well, the velocity is maybe, well, a little v. So it's not the curly v, the space-time v, it's a little v, is g of v delta of lambda. Well, that's at the point where they coincide, delta tau 2, comma, no G, sorry. No G. It's epsilon alpha of the velocity v delta delta of tau 2 E alpha, where alpha now only runs from 1 to 3, and independent of what that is, this is an expansion in only these two, wrong color, in only these two basis vectors of our observer. Do you see that? E1, E2, and the E0 is not part of this expansion. So the resulting vector will lie in this tangent space, okay, somewhere there. But what are the components with respect to E1, E2, and E3? Well, the components selected with an epsilon, and I need to tell you what the epsilon is, and that's subtle, where epsilon 0, epsilon 1, epsilon 2, epsilon 3 is the unique dual basis of E0, E1, E2, E3. Aha, so the observer at each point has a basis of 4 vectors. To this 4 basis, there is a unique dual basis. Of this unique dual basis, we are then only going to use these 3 guys, and then again these 3 guys, in writing down this 3 velocity. Now, sometimes one thinks, well, then epsilon 1, 2, 3 is the unique dual basis to E1, E2, E3. No, because these are vectors in 4-dimensional space. 4 vectors in a 4-dimensional space are not a basis, and there's no unique dual basis. I need to find the full dual basis, and then I pick only these 3. You say, what a terribly ill-defined concept, right? I mean, for another observer, it would look different. Oh, yes, it will. And that's the whole point, because this observer will see this velocity. I don't know whether I should attempt to draw this, but this observer will see this velocity in this space span of this E1, E2, E3, and we'll probably see it somehow like this. This is the V delta, where this is the curly V delta at this point, delta of tau 2. You see? And that is the velocity we speak of in the lab. And now if you know this velocity we speak of in the lab, you can ask, is it smaller or faster than the speed of light, and so on, or what is the velocity of light? Yes?
Did we just define the Curie velocity to be this, or can we somehow connect this to the velocity one classically has a notion of?
Well, the point is, from the way we came, by defining the concepts top down, this is a derived concept. Because what is now objective in relativity, in space-time, this velocity, the yellow velocity, is objective, because the world line is objective. It's in the real world. This is a tangent vector in the real world, right? But this velocity, the 3 velocity, we had to construct with the use of an observer who sees this 3 velocity. Another observer with another frame will extract from the same objective 4 velocity another 3 velocity. Okay? That's it. That's the whole secret to different observers seeing different things. And it's even not very different from classical mechanics, because also there different observers see different velocities. It's only here that because of the cone and the different observers, they can never see a massive particle velocity, well, I would say faster or bigger than the speed of light, but we haven't talked about yet how the metric looks like here. But of course we can do that, right? So you can say that the spatial metric that the observer uses in this tangent space, not in an extended submanifold, but in the tangent space, is of course -1, -1, -1, because it's just the part of G, E alpha, E beta, right? So then if you put a minus sign before it, it looks a little bit more friendly. Okay? So you can then take this vector and measure it with this metric, and then you get a length of this vector, and this length will never exceed 1. Right? So the spatial length of the spatial vector won't exceed 1. And that is what it says. It's slower than, there's an upper limit to velocities you can see. Spatial velocities. But in the space-time picture, it has to do with lying inside the cone. And again, here it is important. Now it's not the charts. Well, the observers are a kind of chart because it's a very localized chart. It's only at one point it's a frame in the tangent space, right? You could maybe extend this to a chart in the manifold, but that's not even interesting. It's only at this one point, these different directions. But again, it's important. This is objective, and this concept is derived from an objective concept, namely the tangent, the velocity of the curve, of the world line. This velocity is a derived concept with respect to an observer. Okay? And so in this velocity also, if you now want to ask how far does this guy run in a millisecond, you can't go very far because then space-time will change and so on. You take the time of this observer and his measure in space of this observer and so on, and you calculate this. Okay? And that is then just the notion of velocity like we know it in this observer's frame. But this is all observer dependent. The objective thing is the world line and its tangent. And the rest is just extraction of information. Right? So one of the issues is getting rid of this notion that you somehow start objectively in 3 space and then you construct the 4 notions out of it. It's the wrong way around. You first have the notions in space-time, they're objective, and then you construct the observer-dependent notions as derived objects. Yes?
We define the small v only as the absolute value of this little arrow you drew.
No. The small v is a vector. This is an expansion in the spaces E1, E2, E3.
It's not covector acting on vector?
It is. This is a covector, the alpha covector, alpha running from 1 to 3, acting on this 4 vector, and then being dotted into here. It is a vector. So this is a vector. It's even a vector in space-time. This v is a space-time vector. It just happens to lie in the span of E1, E2, E3. Yes?
Would you name this postulate T4 to bring it at the same level like?
That's exactly what I intended to do. Thank you. Thank you. Okay. Yes?
Calling this word line objective, isn't it a little bit weird because it's an objective, it's in the real world, and but it would look, if it could look differently if other people in the real world look at this observer.
No.
But
No, it wouldn't. No, it wouldn't. A bird flies by. The bird does what the bird does. And that's what the world line, the history of the bird is the history of the bird. You may picture the history of the bird in different charts, but that's not what's happening. Okay, you may be confused by the fact that I draw a picture, and you can say drawing the picture is already implicitly using a chart or something like this. Okay, so it's a metaphor. That's why I don't like these pictures. So it's a metaphor, right? All these pictures are metaphors, right? Imagine, think of the history of this particle. And that's a curve, an objective curve in space-time. That's the idea. It has an objective velocity and so on. But then come different observers and measure it. And after all, this is a postulate, how the observer sees that. Okay?
I'm somehow surprised that this is a postulate after defining eigentime.
Yes? I could have, if you have eigentime and you have the curvature, the measure in here, it seems like it's a funny postulate. But in fact, what I would need is for an observer at a point, I would need all points which from the point of view of this observer are at the same time, then I could consider curves through here and I could start defining these velocities. But the point is, as I define observer, it just consists of these tangent vectors to this and that direction, and that tells me nothing about what happens in the manifold a little bit away. And in fact, in curved space-time, this is really an issue also of definition, what you actually mean, how far somebody is away. You could define a radar time and stuff like this. No, I mean, imagine, for instance, in curved space-time, or in any space-time, you have an observer, and you have another observer. Say even they go like that. And now, but it's a curved space-time. So now you say, how far is this guy away from me? This is the Earth, and this is a star. Now what you can do, you can send light, but light will maybe run like this, depending on how the cones change, okay? And then the light will be reflected and will come back. And then you can use this radar time, as it's called. It's the time from here to here. You maybe divide it by 2 or something. You can use this as a measure of distance, half this time, okay? But now imagine some vicious entity in the universe removed this point from the space-time. For instance, or put a black hole there or something, right? So then nothing of the sort will happen. And then the result will be this light ray never comes back. How far is the other guy away? Infinitely far away? You see, these ideas of distance and stuff, this becomes it becomes a matter of definition, and you need to think very, very carefully what you actually mean there. So therefore, defining the spatial velocity in the sense like, well, let's first define here space, and then let's look at curves again, and so on, and then use the time, it's not a bad idea, and locally it will probably work, and blah, 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 but this is much cleaner. Because where I am, I know that I am there, then the tangent space is there, I have the frame, and so on. Okay, that's the idea. Yes.
I mean, this, of course, this assumes that you're at the same point. But I mean, in real life, there's always, I mean, the clock is, it's there, right? I'm not at the same point. Could it be that the space is so curved that even if you have a clock there, it doesn't actually, you cannot perform this thing experimentally, or?
Well, if curvature gets very high, it gets more and more difficult. We'll come to that. Okay. Okay, so I need to stop your questions because I have 2 more things to say. Another consequence is the following. An observer, gamma E, will extract quantities measurable in his laboratory from objective space-time quantities always like that. So the prime example for this is, take the F tensor, the Faraday tensor, the Faraday 0-2 tensor of electromagnetism. So in a chart, you have all seen this. FAB is this guy that has zeros here, it's antisymmetric. It has E1, E2, E3 here, minus E1, minus E2, minus E3 here. And it then has the B, 1, 2, 3, 1, 3, minus 2, 2, 3, 1, B1, and then here minus B3, B2, minus B1, something like this, okay? You've seen this, right? The tensor that combines the E and the B field. Well, this is already in a frame. So this is already the F EA, EB of a particular observer. No wonder that different observers see different E and B fields, because this is this, okay? And then of course you can come up with funny ideas like you only look at the E0, E alpha component, and you call that E alpha. And you only look at the E alpha, E beta component, and take then an epsilon alpha beta gamma, and you call that B gamma. That's essentially this extraction, then the other way around. Okay? But this is highly observer dependent. Highly. And here in the epsilon you see some of the funny behavior of the B fields. Okay? So the objective space-time quantity is the Faraday 0-2 tensor, which is unimpressed by charts or observers looking at it. It is what it is. It is what the Maxwell equations say it is. But then if you want to go to the lab and measure it, you measure these quantities because your lab is an observer. Your lab may be rotating, for instance. Then you measure different E and B fields. Okay? So the observer is the intertwiner between the objective quantity in the real world, described by abstract tensors, and the quantities you measure in the lab with respect to your observer frame. That's it. It's perfectly simple. This fully explains the transformation law of the E and the B if you change observer. That's it. One more blackboard, please.
Only a short question.
Yes.
What's this epsilon?
Oh, the epsilon here is again the famous 1, 2, 3 is plus 1 and totally antisymmetric. One has got to be careful. This is a 0-2 tensor. This is a vector and this is a vector for each alpha. So each of these is just a function, it appears. But it's a space-time function. But something that's a space-time tensor in general may be a hypersurface density. Think about this. You've got to be careful. As soon as you start relating things to 3 space, they might change their density weight. We talked about densities before. This is just for the interpretation. Okay, so final is now number 4. I don't know. Role of the Lorentz transformations. Now it's 3. Role of the Lorentz transformations. So the Lorentz transformations emerge as follows. Let gamma E and gamma twiddle E twiddle be observers. With gamma of some lambda or some tau 1 equals the gamma twiddle of some tau 2. Meaning there are 2 observers which at some point of their history meet at the same point. It's very important. Now one of them has this frame, say, E0, E1, E2, and the other one has this frame, E0, twiddle, E1 twiddle, E2 twiddle. That's roughly how that will look like. Okay, let's have these 2 guys. Now, we know. Well, let's for simplicity say their times are chosen such that this is the same time, because otherwise I need to have so many of these guys. Now it is clear that E0 to E1, all taken at time 0, well, all taken at tau equals 0, is and E0 twiddle to E1 twiddle, also taken at tau equals 0, are both bases for the same T gamma of 0 m. Namely, these two are both bases for the tangent space at this point. That's the definition, more or less. That's totally clear. Thus, if they're both bases, I can express the twiddled basis in terms of the untwiddled basis. Is that right? I can change basis by a transformation which I may call lambda. Okay? And this lambda as a matrix is in GL4. It's a general linear map. It's an invertible map. Otherwise, I can't send a basis to a basis. That's what I know. Now, what do we know? We know that G of EA twiddle, EB twiddle is eta AB. Why? Because of the observer definition. But now I can plug in, this is G of, okay, now I can write it in components, GAB, E, aha. Confusing? Ah, yes. I can write it as, oh, hang on a second. No, I don't even want to write this in components. This is now lambda B, lambda M A E M, lambda N B E N. But because this is C infinity linear, well, anyway, linear, I have lambda M A, lambda N B G E M E N. But this, again, by this also being an observer, is eta M N. So I have the condition eta AB equals lambda lambda eta. That is, these lambdas are element of what we usually call the Lorentz transformations. Right? So that means, what is the role of the Lorentz transformation? The role of the Lorentz transformation, so result, Lorentz transformations relate the frames, so first thing, the frames of any two observers at the same point. It's perfectly meaningless to talk about the frame of this observer and the frame of that observer and to say this comes from this by a Lorentz transformation. They live in different tangent spaces. Perfectly meaningless. Lorentz transformations relate the frames of two observers. They do not, it doesn't make any sense in the first place, they do not act on space-time. They act on one tangent space of space-time and relate observers who meet there. Or they act on another tangent space of space-time and they act on observer frames who meet there. This has nothing to do with acting on space-time points. So the lambda mu nu x mu is the new space-time point x twiddle mu stuff is, I dare say, utter nonsense. Right? This just isn't done. Now, you can do this on flat space-time and say all transformations I want to look at are those. Then you greatly restrict to linear transformations, which means you never have to look at gammas if the original space-time was flat and you chose the right chart. But it also restricts you to not being able to go to polar coordinates. And what has that to do with relativity? Absolutely nothing, right? So Lorentz transformations on space-time are a terrible conceptual idea. Just don't do that. They have no place there, right? And then one does that, right, in special relativity, and then one says, oh, in general relativity now allows that these are not only Lorentz transformations, but any transformation. Well, it was already allowed in special relativity. But if that was so, sometimes people say the Lorentz group is replaced by the diffeomorphism group. If you go to general relativity, you now can go to any frame, whereas before you couldn't. Well, you could, but this was nonsense. And even if you say general relativity is where you leave the Lorentz transformations and you go to others, where the Lorentz transformations keep their value where they had their value before. So the Lorentz transformations in special relativity have the same meaning. Well, this is not their meaning. This is nonsense. This is also true in special relativity. If the space-time is flat, this still holds. So both in special and in general relativity, Lorentz transformations relate observer frames at the same point. And on the whole space-time, be it flat or curved, it doesn't matter, general diffeomorphisms can be chosen in order to go to different charts. There is no difference. Hence it's sometimes so dangerous to start with special relativity in concepts of Minkowski vector space as the space of events, because it clouds your thinking. Okay? This is just an abuse of flat space structure. Thank you very much.